At the Department of Low Dimensional Systems of J. Heresky Institute of Physical Chemistry, we work on 2D materials. What is a 2D material? Let's take this piece of material. It has 3 dimensions: length, width, and thickness. If it is a layered material, I can severely reduce its thickness as small as ounce or couple of atoms, known as single layer or monolayer. Thus, the 3D objects become 2D materials with length and width but almost no thickness. There are different methods to produce atomically thin 2D materials. Amongst them, mechanical exfoliation is the simplest. One needs Scotch tape to exfoliate a 3D crystal of stacked monolayers. The advantage of mechanical exfoliation is that it can produce high quality materials with few defects, which is essential for practical applications. However, the major problem is the size of the samples, which is usually in the micrometer range, too small for large scale applications. So what's the solution? Recently, researchers have discovered that some metals can be used to exfoliate millimeters and over 2D samples by exploiting the strong interaction between the metal surface and the desired materials. However, the metal surface must be clean and oxidation-free. Besides, plenty of air-sensitive materials demand inert environments to produce their 2D counterparts and subsequent studies. And here, our UHV exfoliation system comes into the picture. Using this machine, we produce single-layer 2D materials, semiconductors, insulators, magnets, and superconductors by mechanical exfoliation on different metal substrates inside an ultra-high vacuum, in short UHV, where the air pressure is maintained at 10 to the power minus 10 millibar, which is 10 trillion times lower than the atmospheric pressure.
Our main goal when we were designing this system was to reproduce all individual steps, which are usually done during the exfoliation process in ambient conditions in an ultra-high vacuum chamber. Therefore, we have inside the chamber manipulators for sample movement, a heating stage, and an arm to approach it, and a metal evaporator. Thanks to that all components, we can cleave a 3D crystal using tape and from the tape exfoliate monolayers on freshly prepared adhesive metallic layers. The first inspection of the prepared samples can be done in situ using an optical microscope and a simple Raman spectrometer. The machine is versatile because we can easily change crystal, substrate or metal. Furthermore, the main chamber is connected to a load lock chamber for insertion or removal of samples. In case of air-sensitive samples, we can connect a vacuum suitcase and transfer them without breaking the vacuum. On the other side, there is a plasma chamber for cleaning of the substrate.
To prove our system, we started with the exfoliation of MOS2, or molybdenum disulfide, on gold. This has already been demonstrated in air, so it was important to reproduce it in UHV. We obtained monolayer MOS2 flakes of several millimeters in size and of high quality, with few defects only due to the parent MOS2 crystal. More interesting was to demonstrate MOS2 exfoliation on silver. The surface of silver oxidizes fast, so exfoliation in air is challenging. In UHV, we obtained results similar to gold. MOS2 flakes of several millimeters, mostly monolayer and single crystal. So here is where our system proved effective. To confirm the presence of monolayer MOS2, we measured Raman spectra using our in situ spectrometer. The spectra really showed the expected MOS2 features, with only a shift of the Raman peaks on monolayer respect to higher layers. We attribute this shift to strain induced by the substrate that is released in MOS2 layers above the first one. This contributes, we believe, to the monolayer selectivity of this exfoliation method. As mentioned before, we can also transfer the samples to other UHV systems without breaking the vacuum, by using a suitcase. This way, we could also measure XPS and lead, which further confirm the quality of our MOS2. So, with our UHV exfoliation system, we can prepare monolayers of MOS2 and other 2D materials.
This way we can study fundamental studies of these materials in efficient condition using different state-of-the-art techniques. This is prerequisite for an in-depth understanding of their physical properties and potential applications.